Welcome to another one of my lectures on time perception. Today's lecture is going to be examining the relationship between the perception of time and the rate at which we process information. Unlike some of the other lectures I've given on this course, some of the material here is more exploratory and conjecture and hand-wavy, if you like. I'm going to discuss some sound findings that have been found in the literature, but I'm also going to conjecture or kind of think about where there are gaps or where there may be connections which are at the moment unproven, but there are pieces of evidence which point in a particular direction. Fundamentally, I'm going to argue that there seems to be some crucial relationship between our perception of time and the rate at which we process information. Okay, so as I've discussed in other lectures, there seems to be a series of techniques or things that we can use which seem to speed up the internal clock. So the first of these is body temperature. So I discussed Hudson Hoagland and the idea of his wife having flu, having a raised temperature, so her internal clock seems to be running faster. We know that we can also speed up the internal clock with the use of dopaminergic drugs. This evidence is very clear in animals, particularly in rat work done by Mech and colleagues. But this translates less well to humans. We also know that the modality of the stimulus makes a difference. So the internal clock seems to run, for whatever reason, seems to run at a faster rate for auditory stimuli than it does for visual stimuli. It also runs faster for filled intervals rather than unfilled intervals. We also know that boredom or low arousal can slow down the internal clock speed. So if you make an experiment extremely tedious and extremely boring, the longer that experiment goes on for, then the shorter the estimations of duration people will make, as if their internal clock has slowed down. And perhaps the most powerful technique we have for altering internal clock speed is that of repetitive stimulation. So if I present a series of clicks or a series of flickers before a duration to be timed, then this has the effect of making the duration to be timed appear longer. And the fact that we can alter internal clock speed in this manner sort of points to the fact that we have an internal clock at all. But as I said before, the key signature of these effects is that these effects manifest themselves as a slope. Okay, I've covered this before, but I'll quickly go over it again. If you look here, the difference between the red function and the blue line is a difference in slope. The blue line has a steeper slope than the red line. And this means that the difference between the two conditions is getting larger the longer the duration is. And this is consistent with the idea that you've increased the rate of something. And the example I've given before is of two cars leave Manchester at the same time. One's travelling at 30 miles an hour, the other's travelling at 60 miles an hour. The longer they travel for, the bigger the gap between them will grow. And that, if you plotted the distance against time, you'd end up with a slope effect. And this is in contrast to an intercept effect. So if you look at the lines, the green line and the red line, they differ in intercepts. They have the same slope, they are parallel to each other, but they have a different intercept. And by intercept, we just mean where this line would intercept the y-axis if we carried it on. And an intercept would suggest a bias. It would suggest that you were biased in one condition to overestimate duration. But that bias doesn't get larger the longer the duration to be timed is. And there are lots of things which can affect our perception of time in a biased direction, and we're not so much interested in those. What we're interested in is those stimuli which are called slope effects, because those slope effects are mathematically consistent with the idea that you've increased the rate of something, and in this case the rate of the internal clock, or the rate of the pacemaker of the internal clock. Okay, and again, this is actual data here, so this is idealised data, this is actual data. So this is auditory stimuli and visual stimuli, either preceded by clicks or by silence. And even in the average data, you can see that this is a slope effect. In actuality, to prove that, you would have to do individual regressions on each person's data. And then for each person or participant, you would get a slope value for one condition versus the other, and then you do a t-test on that. But the effect is so strong you can actually see it manifest in the average data. As I said before, the visual flickers also work. This effect also works with children, so it's not dependent on some complicated higher order decision process. It seems to be working at a lower level, fundamental perceptual level, and it works across a variety of tasks and clinical populations. So this effect seems to be generalizable. It doesn't depend on one specific task for it to work, and it doesn't work in any other context. It seems to be quite a robust effect. Okay, so that's all very well and good, but as the nature of this course suggests, and from if you're watching this lecture as part of my Perception from Lab to Life course, then we're trying to make connections between the evidence or the data and theories that we come up with in the lab and our everyday experience of time. So let's see if we can make some connection here. So firstly, let's have a little thought experiment about information processing and sense of time. And we can think of different examples here. So imagine you're watching a YouTube video and it's a tutorial for a subject that you know quite a lot about. So you'll be watching this tutorial and you'll be thinking, well, I know this information, get to the point. I know this information, get to the point. And maybe you actually speed up the video. So because you can easily process the information being presented, it seems to you as if the video is going too slow. Now think of an opposite situation. So imagine turning up to an advanced third level course or even a master's course in a subject area that you know nothing about. Maybe quantum mechanics, just to pick an example out of the air. You'll sit down in that lecture, the lecture will start, and very quickly you'll probably be overwhelmed by the amount of information being thrown at you. It will be like, whoa, slow down, give me the information slower. Okay? It will seem as if the lecture is, if you like, going too fast or is in fast forward. Just before we move on, another example of this, which is quite common, is computer games. So there may be a particular computer game, when you first start playing it, it seems as if you're overwhelmed with information. There's too much to do. You can't do it all at once. It seems as if the game's on fast forward. It's like, whoa, this needs to be slower. But then as you master the game, it seems as if the game slows down subjectively. You're able to do far more in any given moment of game time. So let's think about some other situations, perhaps more extreme situations in which people describe time slowing down. So let's think about car crashes or high adrenaline situations. So let's take the example of car crashes. This is quite a common phenomenon that people report when they're in a car crash, that in the last few moments of the crash, as they're heading towards the wall or they're heading towards the other car, they often report that it felt as if time seemed to slow down, as if the moment was in slow motion. And you find this with lots of other high adrenaline situations. So there's a few papers by these authors here, Noyes and Coletti, where they took all these reports of sort of near-death experiences. So car crashes, rock climbers, people involved in dangerous sport. I think they had some cave divers, that kind of thing. And they looked at the kinds of things that they reported. We'll move on to some specifics of those in a moment. Another example is in sports. So people who are elite athletes at high-speed sports, so an example would be tennis or squash, say that when they're really on it, when they're fully trained and experienced and in form, they often describe this sensation of being in the zone. And if you probe what they mean by this, they'll say, well, it feels as if my opponent is playing in slow motion, and I have all the time in the world to observe what stroke he's going to make, and I have all the time in the world to decide exactly what stroke I'm going to make in response. Okay, so there seems to be, again, this link between the rate at which we can process information and our perception of whether the world is going in fast forward or slow-mo. But we have to be a bit careful here about what people are actually describing. So here's a nice quote from the Noyes paper, where they ask these people to report these near-death experiences or dangerous experiences that are in. And this is a useful quote. So, my mind speeded up. Time seemed, let's move me out of the way. Time seemed drawn out. It seemed like 5 minutes before the car came to a stop, when in reality it was only a matter of seconds. Now this is the important bit. As well as reporting this slowing down of time, Noyes also found that people commonly reported a heightened sense of touch or hearing or vision. And this is reflected in this quote. So the second half of the quote says, "I remember that my sense of touch and hearing became more acute. I was unusually aware of my grip on the steering wheel and of my body touching the seat behind me. The grass brushing the door was unusually loud." Okay, so we see both there. Time seems to slow down and a heightened rate of information processing, if you like. But we have to be careful what it is that people are actually reporting here. So here we have a very clear example where both time perception and rate of information processing seem to be locked together. But there are other possibilities here that we have to consider. So let's go back to the car crash example, or some of the examples in the Noyes paper of people rock climbing and falling. So people report this phenomenon of time seemed to slow down, or some variation of that. Well, there are several things that this could be referring to. If you think about having a car crash or some other traumatic, dangerous experience, then it's likely to be something that you think over and over again. You kind of over-process it. And it might be a story that you relate to, an anecdote that you relate to people over and over again. And it might be in that retelling or rethinking of the event that the event gets embellished, that you start adding in details that weren't actually there at the time, but you somehow remember them. They become part of your memory of the event. So that few seconds of the car crash gets stretched out in your memory. Secondly, it could just be a temporal phenomenon. It could be that your sense of time does slow down. That is, your internal clock speeds up in this situation. Okay, you get an enormous jolt of adrenaline. You're massively scared or aroused, emotionally aroused by the event, and this speeds up your internal clock. So the rest of the world, in contrast, seems to be slow. But that's all it is. You're kind of frozen in the moment. Although your brain is seeing the world in slow motion, you can't actually act any quicker. The third possibility is that you have both going on. Both your internal clock is sped up and your brain can take in information quicker. Okay? So as in this quote, your sense of touch, your sense of hearing, your visual processing gets sped up and the world seems to slow down. What the causal relationship is between those two things, we'll discuss it in a little while. But again, you can't actually act any quicker. And then fourthly, we're sort of building up here, maybe you can actually act quicker. So your internal clock is sped up, you process information more quickly, and you can act more quickly. And you can see why there would be a survival imperative for this, why evolutionary it might be advantageous for you in these high adrenaline situations to both be able to think more quickly and act more quickly. And in turn, this may make the world seem as if it's slowed down. It may speed up your internal clock. Or maybe what's actually happening is it's speeding up your information processing, which in turn makes the world seem slow. We'll discuss these different causal relations in a moment. So this leads us to an interesting question. Is brain time the same as clock time? Do events occur in clock time, or do they occur in brain time? Or in other words, is the rate at which you process information determined by clock speed? But maybe you have some master internal clock, just like a computer clock, which controls the rate at which you process information and also controls the rate of your internal pacemaker, of your internal clock. Or maybe the internal pacemaker of your internal clock also controls the rate at which you process information. There are causal relationships here which are difficult to disentangle, but maybe the things which I'm pointing out point to there being a connection between these two things, regardless of what the causal relationship is or the causal direction is. And again, another quote from the Noyes paper: "My thinking processes increased at an incredible rate, so that my movements in relation to them seemed extremely slow." So this is pointing to a more nuanced picture. So this is kind of pointing to 2 and 3 here, but not 4. So you're processing information more quickly, but the rate at which you're acting seems slow. So maybe that's lagging behind. Okay, so how might we investigate this empirically? Well, obviously, for ethical reasons, it's very difficult to put people in genuinely dangerous situations and see how that affects their information processing and how it affects their perception of time. But there have been some attempts at this. So there's quite a famous or infamous experiment that keeps cropping up in the literature. It's actually quite annoying how often this crops up because it's not a very good experiment, as I'll explain in a moment. But the concept is good. So there's an American neuroscientist called David Eagleman who occasionally dabbles in time perception. And what he had is he had people in this cage here that was hoisted up into the air on a crane, and people are attached by a rope, and they make a free fall into a cargo net. And what happens is that strapped to their wrist is a digital display that quickly flashes up a 2-digit number. And before they go up in the cage, this is calibrated so that the number flashes up at a rate which is just too quick for them to reliably tell what the two numbers are. They're then taken up to the top of the crane, they jump off the crane, and the idea is that their adrenaline increases, and this speeds up their internal clock. And if this speeds up their internal clock, then it should make the external world seem slower. And if it's making the external world seem slower, or increasing the rate at which they can process information, then this briefly flashed up number should last subjectively longer, and they should be able to now read this number that they couldn't read when they were on the ground in a calm state. David Eagleman called this thing that was attached to their wrist as the eagle eye. Okay, good old American self-publicity there. Now, despite the reports of this experiment, in actual fact, if you look at what happened, there was no evidence of a reduced visual temporal threshold in freefall. It didn't help them to see the number. They only had 20 people doing this, so it's a very weakly powered experiment. He also got them to make duration judgments as well, but only 7 of them were asked to do that. And one of the participants kept their eyes closed for the entire fall. So this is quite a weak experiment. There's also another problem with this, is that the spatial control is weak. Well, what do I mean by that? Well, in normal circumstances, if I flash an image very quickly at you, on a computer screen for example, then you have what's called persistence of vision. So even though I may only flash up that number for, say, I don't know, 50 milliseconds, it will persist in your vision for longer than that. It's what's called iconic memory. So it will persist in your vision up to 120, maybe 200 milliseconds. To get around this, what we have to do is present a mask immediately after presenting the number. So after presenting the number, in Eagleman's case, he presented the same number but in inverted colours. Okay? Another way of doing it is to simply present a scrambled field immediately after presenting the number. What you can't do is just present a black or a dark screen, because then you will have iconic memory, you will have this persistence of vision. But if you present this mask, it kills off or terminates this persistence of vision. So you actually have control over how long that digit is actually being exposed to the brain of the person. Now, on the ground, when they're stationary and they're staring at this number, then that's not a problem, because the mask is in the same visual area as the number that's just been presented. However, if they're plummeting to this cargo net, their arm is going to be moving all over the place. So the mask is not going to be in the same visual part of space as where the number was presented. So it's highly likely that they're going to more likely to be able to see the number because of persistence of vision. So we don't have this spatial control. So even if Eagleman had found the right result, then it's likely that it would have been due to this lack of spatial control. Just for amusement, there were some early attempts at a similar thing. If you go back to the 1960s, there's some great wacky papers. And there's one paper by Langer which I found. I love this diagram that's in the paper. And here people are being wheeled towards the edge of a staircase, and as this happens, they're asked to make timing judgments. And this had the effect of making them fearful, which sped up their internal clock, which made them make longer duration judgments. Although there are many problems with this experimentally, but some attempts had been made at it before. So yeah, it's worth having a look at this paper. It's quite interesting.